6-1. Use similar polygons. By the end of today's lesson, we will be able to successfully use proportions to identify similar polygons. Similar polygons, by definition, just means corresponding angles are congruent and corresponding side lengths are proportional. Example 1. In the diagram, triangle ABC is similar to triangle DEF. Part A. List all pairs of congruent angles. So angle A corresponds with angle D. Angle B corresponds with angle E. And then we have angle C corresponding with angle F. Now part B, check that the ratios of corresponding side lengths are equal. So I'm going to check AB to DE, which is 10 to 15. And then I'm going to check BC to EF, 8 to 12. AC to DF, 12 to 18. And now after we simplify this, we get the same ratio, 2 to 3. So they're equal to each other. In part C, I would like you to write the ratios of corresponding side lengths in a statement of proportionality. So first, you look at the first triangle, ABC, and you take AB, and you set it as a ratio with DE. And you do it the same thing to the other two pairs of sides, BC to EF, and then you have AC to DF. Example 2. Determine whether the polygons are similar. If they are, write a similarity statement and find the scale factor of ABCD to JKLM. So when we write a similarity statement, you need to state all the angles congruent as well as the sides, the ratios of the sides. So first, let's look at the angles. As you can see, angle A corresponds with angle J because they're right angles. Go ahead and write angle A congruent to angle J. And if you look at angle B has one arc and angle K has one arc. So that just indicates that angle B is congruent to angle K. And the same goes for angle C is congruent to angle L, and then angle D is congruent to angle M. Now we need to look at their sides now. So first I'm going to look at AB to JK, which is 8 to 14. AB to JK. And let's look at BC to KL, which is also 8 over 14. BC to KL. And then we have CD to LM, which is also 8 over 14. CD to LM. And then we have DA, which is 12. DA to MJ. So 12 over 21. And if we simplify these ratios, we should get 4 to 7. And 12 divided by 3 is 4. So all three ratios are equal to each other. So we can state that these two quadrilaterals are similar, and we have our similarity statement. And then the scale factor would just be taking any of these ratios here, so it's just 4 to 7 for all of them. And this would be the scale factor of quadrilateral A, B, C, D to quadrilateral J, K, L, M. Example 3. In the diagram, triangle BCD is similar to triangle RST. Find the value of x. So in this case, we need to set up a proportion. 12 BC, 24 RS. That would be our first ratio. And then we can take the corresponding side of CD to ST. And then we can solve. And X would be 26. Example 4. In the diagram, FGHJ is similar to LM and P. Part A. What is the scale factor of LM and P to FGHJ? So we're going from this figure to this figure. So I can take any of these, 12. I'll just take 12 and then put it over 15, the corresponding side of PN, which is JH. And then I can simplify this. Then my scale factor is just 4 to 5. So you need to pay attention to which figure is stated first when you find the scale factor. Part B, find the value of x. So I can take the scale factor from part B, 4 to 5, and put it over, or set it equal to x over its corresponding side length of 40. And I could first simplify and then do a cross multiply. So x is 32. Theorem 6.1, perimeters of similar polygons, states that if two polygons are similar, then the ratio of their perimeters is equal to the ratios of their corresponding side lengths. So this means that if KLMN is similar to PQRS, then the perimeter of the first figure, KL plus LM plus MN plus NK, to the perimeter of the second figure, PQ plus QR plus RS, and then SP would equal to the corresponding side lengths. And there's a proof for this on my website, and then if you're interested in why, please visit my website under chapter 6.1. So we could set this equal to KL to PQ, and then LM to QR, and then we have MN to RS, and then lastly NK to SP. Example 5. A larger cement court is being poured for a basketball hoop in place of a smaller one. The court will be 20 feet wide and 25 feet long. The old court was similar in shape, but only 16 feet wide. Find the scale factor of the new court to the old court. So the new court here, let's see, and then the old. So the new one is 20 feet wide and 25 feet long, and the old court is only 16 feet wide, and we want to find we want to find the scale factor from the new to the old. So we could just take 20 to 16 and simplify to get 5 to 4. And part B wants you to find the perimeters of the new court and the old court. So we need to first find the length of the old court by using proportions. So 20 to 16, we've already simplified it. It's 5 to 4. And we need to set it equal to, let's make this x, equal to 25 to x. And we can simplify. So x is 20. So this is 20 here. And then we can, for the new court, the perimeter would then be twice the sum of 25 plus 20. So this is 45, which, and then this will equal to 90. And then the old twice 16 plus 20, so that's going to be 72. And let's not forget to label corresponding lengths in similar polygons. If two polygons are similar, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor of the similar polygons. So that's a quick review. And example 6 in the diagram, triangle FGH. FGH is similar to triangle JGK. Find the length of the altitude, which is the height of the bigger triangle, GL. Let's first look at the smaller triangle, JGK. We know that the altitude or the height is 14. So we could put 14, and then the base, which is 5 plus 5, 10. We could set that equal to the entire height of the bigger triangle, or the altitude, GL, and then put it over the length of the base. And then we can solve for GL. So then 5 GL would equal to, and GL would equal to 22.4.